A charge of 8 microcoulombs is at the origin, and a second charge of -4 microcoulombs is on the x-axis, 9 meters from the origin. Find the electric field at a point on the y-axis, 7 meters from the origin. So we've got things on our x and our y-axis. So we've got our y-axis, got our x-axis, and one thing we know is that at the origin, there is a charge of 8 microcoulombs. So I'm going to go ahead and label that charge Q8. We also know there's a second charge of -4 microcoulombs on the x-axis, 9 meters from the origin. So I'm going to count over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So at 9 meters over, we have a charge of -4 microcoulombs. Okay? And then we want to find the electric field at a point that's on the y-axis, 7 meters from the origin. So 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to go up 7 meters, and this is where I want to find the electric field. Now there's no charge there, but there's still an electric field at this spot. So let's go ahead and get started by finding the electric field at this point from the 8 charge and the electric field from the -4 microcoulomb charge. So let's go ahead and find the electric field from the 8 microcoulomb charge first. So the electric field from the 8 microcoulomb charge is Coulomb's constant 8.99 times 10 to the 9th times 8 microcoulombs, so that's times 10 to the -6, over the distance squared, which is 7 meters squared. Go ahead and solve this, and we find that we get a magnitude of 1,467 and 76 hundredths newtons per coulomb. Now the next thing we need to do is decide what direction the electric field is going to point. Well, the electric field points away from positive charges. So if I'm here and I'm pointing away from the positive charge, I'm pointing straight up. Okay, so the 8 microcoulomb charge creates an electric field of 1,467 and 76 hundredths newtons per coulomb in the upward direction. Okay, next we're going to find the electric field at this point due to the -4 microcoulomb charge. So, the electric field due to the 4 microcoulomb charge is again Coulomb's constant, 8.99 times 10 to the 9th, times the charge, and we leave the negative out because that's just going to tell us direction later, so 4 microcoulombs, 4 times 10 to the -6, divided by the distance squared. We need to find the distance here. Well, I just made a right triangle, okay? So this side was 7 meters, this side was 9 meters. We need to know this side over here, which we can go ahead and call C. Pythagorean theorem, a squared plus b squared equals c squared. So 7 squared plus 9 squared equals c squared. We're going to end up with C is approximately 11 and 40 hundredths meters. Okay, plug that in down here, 11.40 squared, and we find that the electric field created by the 4 microcoulomb charge has a magnitude of 276.7 newtons per coulomb. And remember, electric field lines point toward negative charges. So toward this charge. Well, that means it's going to be going down and to the right. And we want to find the overall net charge at this point, okay, which means we need to add these vectors together. Well, the vector that's going straight up, not too bad, but then we have this vector that's going down and to the right. So we're going to break that into its components, okay? And to do that, let's go ahead and take a look at what we need to do. First, we need to figure out what these two components are. We know the magnitude is 276 and 7/10. So we know the magnitude of the electric field that's going down and to the right, but we need to know these components, the perpendicular component of the electric field and the parallel component of the electric field. And to do that, we need to know more about this triangle. Okay, we need an angle other than just this 91. We need one of these two. So I'm going to label the angle up in the top here, theta. Now that angle is the same as this angle that we've got created by the side lengths. So we can go ahead and find that angle using some trigonometry. So we're going to say the tangent of theta is equal to the opposite 9 over the adjacent 7, inverse tangent to both sides, and we'll cancel there. We'll be left with our angle is 52 and 13/100 degrees, and that is the same angle over here. Now we can continue using some trigonometry to find the sides. Well, let's find this parallel side first. This is the opposite, and we know the hypotenuse with this angle, so we're going to say the sine of 52 and 13/100 is equal to the opposite, the parallel component, over the hypotenuse, 276.7. Multiply both sides by 276.7, and we get the parallel component is 218 and 43/100 newtons per coulomb, and this component is pointing to the right, so to the right. Similarly, we're going to find the perpendicular component. Well, this is the adjacent side, so we'll use cosine. So the cosine of the angle 52 and 13/100 is equal to the adjacent, in this case the perpendicular component, over the hypotenuse, 276 and 7/10. Multiply both sides by 276 and 7/10, and we get the perpendicular component to be 169 and 86/100 newtons per coulomb, and that is pointing downward. So this is broken into its two components. We have the parallel component, 218.43 newtons per coulomb to the right, and we have the perpendicular component, 169 and 86/100 newtons per coulomb down. And now we are ready to do some vector addition. We are going to add this vector because it's completely in the vertical direction, and then we're going to add the two components of this vector, okay? We're not going to include this anymore because we broke it into its two components. So we're going to find the net electric field in the x direction. Well, that's the y direction, x direction, y direction. So we only have one x direction, so when we add them up, it's pretty simple. We just get what we have, 218 and 43/100 newtons per coulomb, and that is to the right. Then we're going to find the net electric field in the y direction. Well, now it's a little bit more difficult. We have 1,467 and 76/100 newtons per coulomb up, so we're going to let that be positive, plus 169 and 86/100 newtons per coulomb down, so we'll make that negative, which means the net electric field in the y direction is 1,297 and 9/90 newtons per coulomb up, because the positive was greater. So we're going to add them together using vector addition. So first, we're going to go over 218 and 43/100 and then tip to tail, so we start where we finished. We're going to go up 1,297 and 90/100 newtons per coulomb, and we're going to find the resultant vector. Okay, so now we are ready to use the Pythagorean theorem to find the net force, the net electric field in this triangle here. So, if you look at this, I've got a right triangle, and that is the hypotenuse, so I can solve using Pythagorean theorem. A squared plus B squared equals C squared. So in this case, we have 218.43 squared plus 1,297 and 90 hundredths squared is equal to the net electric field squared. If we solve, we're going to get the net electric field is equal to 1,316 and 15 hundredths newtons per coulomb. We're still missing the direction. So we need to find the direction. Well, it's going up and to the right. So I'm going to label the angle in the picture. It's important that we label the angle so that it is included. And then we're going to find that angle using some trigonometry. So I know the opposite and adjacent, so I could use the tangent function. So the tangent of the angle is equal to the opposite, which is 1,297 and 90 hundredths, over the adjacent, 218 and 43 hundredths. And then to solve, I have to take the inverse tangent of both sides. And I will get that my angle is 80 and 45 hundredths degrees. So, and then I can draw that over here. And I have my angle in the original picture. Okay, so theta is equal to 80.45 degrees.